Right. In part one of this session, we discussed about multidimensional signals, which were baseband, and we looked at methods to construct multidimensional signals. And particularly, we looked at two methods, which were one was to have it in a non-overlapping fashion, and the other one was to have it as an overlapping set of signals, right? And then we also talked about the signal space representation of those signals, and then we showed that when you have those non-overlapping orthogonal signals, the signal space representation contains vectors which lie on the basis functions, that is, they lie on the axis of the m-dimensional space in which they belong. So that was the baseband representation of multidimensional signals, and we also talked about why we need to have multidimensional orthogonal signals. Why can't we just have m signals in a two-dimensional space rather than having m signals in a multidimensional or m-dimensional space? The reason is because if we have all the signals to be orthogonal with respect to each other, then the error probability for a given signal to noise ratio becomes smaller as we increase the value of m. So that means we can transmit at a higher rate as well as have lower error probability if we use orthogonal signals. So therefore it makes sense that we develop multidimensional signals, that is which are orthogonal with respect to each other. Okay, so the previous session was restricted to multidimensional signals which were baseband. Now we will continue that discussion and take it further and consider bandpass signals which are multidimensional, and we will go on to show that if we construct our bandpass signals using orthogonal baseband signals, then the resulting bandpass signals would also be orthogonal. Okay, we will see that, and then we will see one simple method of creating orthogonal multidimensional waveforms by having orthogonality in the frequency domain rather than in the time domain. Okay, we'll talk about all those details in this session. Okay, so let's first start with what is bandpass signals. So in bandpass we use some carrier signal to shift the spectrum of the baseband to some higher frequency, so that gives us a bandpass signal. And generally, how do we produce a bandpass signal? One way is to simply multiply the baseband signals with a carrier signal which has some high frequency Fc. So that will result in the spectrum of the baseband signal being shifted to a frequency band which is around the carrier frequency Fc. So we can create bandpass signals by multiplying the baseband signal, which we have denoted here as Sm of t, with a carrier signal of some frequency, high frequency Fc. And the notation we are going to use for the bandpass signal is Vm of t. So we have capital M such bandpass signals corresponding to that many baseband signals. Okay, so we multiply the baseband signal with a high frequency carrier signal to get our bandpass signal. Now the first thing we are going to show is if we have these baseband signals orthogonal to each other, then after multiplying with the carrier, the resulting bandpass signals would also be orthogonal with respect to each other. So let's see that proof over here. So the dot product of any two bandpass signals, if we call the two bandpass signals as say Vm of t and Vn of t, is simply the inner product between them integrated over the interval 0 to t. So that's simply the signal m is called Vm of t is Sm cosine 2 pi fct and Vn is Sn cosine 2 pi fct. So we multiply this. So this is of the form Sm into Sn into cosine. So that's cosine square. So we have Sm of t into Sn of t into cosine square 2 pi fct integrated from 0 to t. and we can use the trigonometric identity for cosine square x or cosine square theta as 1 plus cosine 2 theta by 2. So cosine square 2 pi fct is 1 plus cosine 2 pi into 2 fct, that is cosine 4 pi fct by 2. That by 2, the factor has been inserted outside the integral here. So then we multiply the terms, so we get sm sn into 1 plus sm sn into cosine 4 pi fct. So let's simplify that. So we get these two terms. This is the term that you get when you multiply with the 1. This is the term that you get when you multiply with the cosine 4 pi fc, that is the double frequency term. Okay, so we have seen this in a couple of times previously, also in our earlier lectures, that the high frequency, when this fc is large, the double frequency term, this integral becomes 0 when the bandwidth of the baseband signals is smaller compared to the frequency fc, which is true in this case because fc is the carrier frequency, which is a large frequency. So this this term, which is the double frequency term, completely vanishes. So we are left out with only this part of the equation. So the dot product of any two of the band pass signals Vm and Vn is equal to half the dot product of the corresponding baseband signals which were used to produce those band pass signals. So if the baseband signals Sm and Sn are orthogonal, that means this integral would evaluate to 0. So that means this whole thing will be 0, and correspondingly this is equal to 0. So what we have is that if the baseband signals are orthogonal, then the resulting bandpass signals are also going to be orthogonal. So if we start with our ppm signals, which are orthogonal signals, and produce baseband signals using those ppm signals by multiplying those ppm signals with our carrier signal, then the resulting bandpass signals would also be orthogonal. And when we have this m is equal to n, when we put m and n to be the same, so that will be Vm into Vm, which is Vm square of t, integrated from 0 to t, and Sm into Sm, which is Sm square of t, which is, so basically these integrals are nothing but the energies of the corresponding signals. That is the energy of the signal Vm of t, and that is the energy of the baseband signal Sm of t. And again, this is a relationship which we are familiar already from our previous discussions, that the energy of the bandpass signal is half the energy of the baseband signal. So which is what has been proved here. So we notice two things happening here, that when we produce baseband signals, even in the multidimensional case, not baseband, when we produce bandpass signals, even in the multidimensional case, then what we notice is, if we start off with orthogonal baseband signals, it gives orthogonal bandpass signals. So if we have orthogonal baseband signals, we have orthogonal bandpass signals. And the other fact is that when the signals are same, that means the energy of the bandpass signal is half the energy of the baseband signal. Okay, so since our ppm signals, which we discussed in the first part of this session, are orthogonal, the resulting bandpass signals would also be orthogonal. Now the other thing we have to notice here is that the ppm signals we started off with, they are orthogonal in the time domain. Okay, and that orthogonality arises by virtue of being non-overlapping. They are orthogonal because they are non-overlapping, and they are defined for time intervals or durations which do not overlap with each other, and therefore their orthogonality is in the time domain. Now our task is to identify how do we produce orthogonal bandpass waveforms. So we need to identify or develop a mechanism to produce orthogonal bandpass waveforms. One way is to simply use these baseband signals and then multiply these baseband signals with a carrier. But a simpler way of doing it is to directly have carrier signals which are of different frequencies, and then we have to select those frequencies in such a way that the carrier signals of different frequencies become orthogonal with respect to each other. The amplitudes are same. The only thing that is different between the signals is their frequencies, and by virtue of their frequencies we can make them orthogonal. So we have to choose the frequencies appropriately, and then the same carry the cosine wave or carrier signal but of different frequency. By choosing appropriate frequency separation or frequency values between the signals, we can make them orthogonal with respect to each other. So that would be a simpler way, rather than using starting off with the baseband signal and then multiplying a carrier. We start off directly with producing carrier signals of specific frequencies, but the trick is to choose the frequencies in such a way that the carrier signals become orthogonal to each other. So this is called as having orthogonality in the frequency domain. So previously in the baseband, the non-overlapping ppm signals that we saw, they are orthogonal in the time domain. So what we are going to see here is called as orthogonality in the frequency domain, and the corresponding modulation scheme or the bandpass signals that we get as a result of such a scheme are called as carrier frequency modulated signals. And in particular, when we use square wave signals, then we call it as frequency shift keying. Okay, when we use rectangular pulses, that is, okay, the carrier frequency modulation is called as frequency shift keying. Okay, so what is frequency shift keying? In frequency shift keying, which we abbreviate as FSK, suppose we are transmitting two symbols, a 0 and a 1. So we transmit the 0 as a carrier signal of some frequency called F1. So it is cosine 2 pi F1t, and it has some amplitude. And the 1 is transmitted as another frequency, which we can call as cosine 2 pi F2t, again of some amplitude. So the two signals are differentiated. That means the 0 and the 1 is distinguished by virtue of their frequency of the carrier signal. So if the received signal is having a frequency F1, the receiver will interpret it as a 0, and if the received signal is having a frequency F2, it will interpret it as a digital 1. Similarly, we can extend this idea to m such symbols. So if we combine bits as say 0, 0, 0, 1, 1, 0 and 1, 1, that gives us m equal to 4 symbols. So with 4 symbols, we need 4 different carrier frequencies, F1, F2, F3, F4. So this way we can create multiple carrier signals, and we can choose the frequency separation between the carrier frequencies between F1 and F2, and if we have 4, between F1, F2, F3 and F4, in such a way that the dot product between the first carrier and the second carrier becomes 0, and therefore they would become orthogonal. In every other sense, these two carriers are identical. Their amplitudes are same, their phase is same. The only difference is the frequency values. So by choosing appropriate values of these frequencies, we can have orthogonal signals. So we can create m-dimensional orthogonal bandpass signals in such a way, which we call as frequency shift keying. Now the frequency separation between the two frequencies, that is the difference between the two frequencies, we call this as delta f, the separation of frequency between any two successive frequencies. So in the case of binary, which is m equal to 2, we have only two frequencies, f1 and f2. If m is equal to 4, it is like then we have a 4-dimensional signal in a 4-dimensional space, each having its own frequency, that is f1, f2, f3, f4 and so on. So what we will see is that with the FSK signals, all of them have equal energy because we are keeping their amplitudes to be the same. Okay, we will choose that amplitude in a specific way, and then only play with the frequencies. Our information is now contained in the frequencies of the signals. So we denote that the signals all have equal energy, which we call as E, for the baseband signals. And from that we will move on to have the bandpass signals, which will be represented by their frequencies. So when we have a baseband signal whose energy is E, and if it is if the baseband signal is a rectangular pulse shape, then that energy is uniformly distributed over the interval or over the interval duration of the pulse, which is t. So the amplitude becomes E by t under the root, because the energy is square of the amplitude. So the amplitude will become square root of E by t. That means the energy is uniformly distributed throughout the duration of the pulse, which is from 0 to t, which is a duration of t seconds. So E by t under the root, that gives you the rectangular pulse representation. Okay. Now we can write this representation in terms of the bandpass energy. So since we know that the bandpass energy is half the baseband energy, so the E here denotes the baseband energy, and we want to write this E in terms of the bandpass energy, because we are now dealing with the bandpass signals, which we denote as Vm or Vn of t. So the notation is V. So we'll call the energy of the bandpass signal as EV, and the energy of the baseband signal is E. So the relationship between the two is that the baseband energy E is 2 times the bandpass energy EV. So we can substitute for the pulse amplitude in terms of the bandpass energy, because we are going to use this amplitude for our bandpass signal, which is the carrier signal of a certain high frequency. So the energy in terms of the bandpass energy is 2 EV. So therefore the amplitude of this pulse, which is square root of E by t in terms of the baseband energy, is now square root of 2 EV by t, where EV is the bandpass energy. So we can now represent our bandpass signals or FSK signals for the binary case, which is called as binary FSK, binary frequency shift keying. So in this case we represent a 0 as a certain frequency f1 and a 1 as another frequency f2, and the frequencies are chosen such that they are orthogonal to each other. So how do we choose the frequencies? What is the condition that will make them orthogonal? We will see that in a little while. So basically the carrier is having a frequency f1 and f2, but the amplitudes, because we are talking about the energy in terms of the baseband energy, and we are writing the baseband energy of this carrier signal in terms of the bandpass now. So the bandpass energy is half the baseband, therefore the baseband energy is 2 times the bandpass energy, right? So it's 2 EV by t. So that becomes the amplitude of our carrier signal. And similarly for the binary one, we have another carrier signal of a different frequency but having the same amplitude as the carrier for 0. So the information is contained simply in the frequencies of the signals, and because f1 and f2 are some large values, so these are bandpass signals. f1 and f2 are basically the carrier frequencies fc and fc plus delta f. So the separation between the two frequencies is delta f, right? Okay, so that is binary frequency shift keying, which we call as binary FSK. Now the thing that you need to note here is that the time interval here represents the total symbol time, and in this case, in the case of binary, one symbol is equal to 1 bit. So the time duration that you have here is basically the bit duration, because for the binary case one symbol is 1 bit, one pulse is 1 bit. So one symbol duration corresponds to 1 bit duration, and since this is the bandpass signal energy representing the complete pulse, and since one pulse pulse duration represents the bandpass energy here, and because one pulse is representing one bit, so this EV also corresponds to the bit energy. So we can rewrite these equations as in terms of the bit energy and bit duration as 2 EV by TB. Okay, so basically for the binary case, the general equation is EV and T, but for the binary case, the energy EV becomes equal to the bit energy, and the duration T becomes equal to the bit duration, which we call as TB, right? So we have the same equation just with these energy and duration represented in terms of the bit energy and bit duration. But if it is MRE FSK, that is multi-dimensional FSK, then we have the duration of each pulse interval, or the energy of each pulse of each symbol, is basically distributed among all the k bits, because in MRE each symbol is k bits long. For example, if we have, say, m is equal to 4, capital M equal to 4, then you have 4 symbols, which are 0 0 0 1 1 0 1 1. So the number of bits in each pulse is going to be 2. So the energy here is for 2 bits, right? So EV is 2 bits times the bit energy, or the bit energy is basically this bandpass energy divided by the number of bits in that particular symbol duration. And similarly, if we have one pulse of duration T representing 2 bits, that means the duration of each bit is half of T by 2, right? So similarly, in general, for any value of M, if we have certain M, then the number of bits in each pulse is k, which is logarithm to the base 2 m. So therefore we can have this relationship between the energy of the symbol and the energy of the bit. So the symbol energy is k times the bit energy, because each symbol is k bits long, and the symbol time is k times the bit time, because each symbol is k bits long, right? So we just write it in a general way using the symbol energy and symbol time. But in the case of binary, the symbol energy is equal to the bit energy, because one bit is one symbol, and the symbol duration is equal to the bit duration, because one bit is equal to one symbol. Okay, let's move forward. The whole idea here is to create multi-dimensional orthogonal signals, and we are trying to create orthogonality by choosing appropriate frequencies for the baseband signals f1, f2, f3, f4, f5, and so on up to m such values. We want to create those frequencies in such a way that their inner product is 0. That means they become orthogonal. So the idea is that the separation between the frequencies, which is delta f, has to be chosen in a specific way. So we'll investigate how we can do that. How do we find the separation, the delta f, which will make the carrier signals orthogonal with respect to each other? But remember, the orthogonality that we are achieving here is in the frequency domain, because we are choosing appropriate frequencies that will make the same carrier signal orthogonal, right? It's the same cosine 2 pi ft, but we are choosing f to be different values such that the two values become orthogonal to each other. Okay, so what do we do to find the condition for orthogonality? We create a measure of similarity between the two waveforms, because the ultimate aim is, when we send our bits or symbols using such orthogonal waveforms, at the receiver side we should be able to separate them out and identify what was the transmitted symbol. So to do that, we need to calculate what is the measure of similarity between any two waveforms which are bandpass FSK waveforms. So if we call one particular waveform as Vm of t and another one as Vn of t, we want to find the inner product between them, and we want to make that inner product to be 0, so that the two signals will become orthogonal to each other. Now we simply introduced this term here, 1 by EV. It's just a normal, it's a factor that has been introduced to cancel out the EV that we're going to get in this product. Because if you notice our representation for Vm of t, it's got a root EV in the numerator, right? So when I multiply Vm with another Vm, so root EV into another root EV, it will become EV. So that is simply the energy of the signal, and because we have all signals to be equal energy, that is not going to affect the orthogonality, right, the inner product. So to get rid of that EV and to simplify our calculations, we include this 1 by EV parameter in front of the integral, and as you will see in the calculations, this will cause the EV term to disappear from this whole equation when we evaluate this parameter, which we call as gamma mn, that is the measure of similarity between any pair of FSK waveforms. So if I have, say, for m equal to 8 FSK waveforms, each having its own frequency, say f1, f2, f3, f4 and so on, the separation between f1 and f2 is delta f. The separation between f2 and f3 is also delta f, so they are spaced by an amount of delta f. So we want to find out what is the measure of similarity between any two waveforms for different frequencies, and using that we will find some condition which will give us how do we choose the delta f which will make our signals orthogonal with respect to each other. Okay, so let's compute this gamma mn term, gamma mn measure of similarity, which is simply 1 by EV, that's the scaling factor, into integral Vm of t into Vn of t. So Vm is cosine 2 pi fc plus m delta ft. So any arbitrary signal from the m signals, because each signal is fc plus m delta f, right? So when m is 0, it is simply fct. When m is 1, it is fc plus 1 delta ft. When m is 2, it is fc plus 2 delta ft, and so on and so forth. So frequency number m is basically cosine 2 pi fc plus m times delta f t, and the Vn of t term is fc plus n times delta ft, right? So we just take the calculation here with using some basic trigonometry and solve for this equation. So when you multiply these two terms, the square root will vanish, so it will be simply 2 EV by t, and the numerators EV and denominators EV will cancel out. So that's why we introduced this term EV, because it will help us to make our calculations simpler. Okay, now these are constants which can be taken out of the integral, and we have this term and this term, which is cosine A cosine B. So we apply the cosine A cosine B trigonometric identity, and which is cosine A minus B plus cosine A plus B by 2. So applying that trigonometric identity, this is what we get. The cosine A minus B part will result in the FC term being cancelled out, and the cosine A plus B part will result in a double frequency term with 4FC. So we have, this is cosine A minus B plus cosine A plus B by 2, that 2 factor we have introduced here in the denominator. And then this EV, as I said, we introduced this 1 by EV factor so that we can get rid of this EV. So the entire EV disappears. So what we are left out is with just 1 by t times cosine 2 pi fct, and minus 2 pi fct will cancel out. So we are left with cosine 2 pi m delta ft minus cosine 2 pi n delta ft. So taking the common terms, you get 1 by t cosine 2 pi m minus n delta ft for the first part of the equation. The second part of the equation is going to have an m plus n term, but which is centered on the frequency of 2fc. Again, like in the previous case, when the frequency is large, this double frequency term will cancel out, okay, will vanish. So when the scatter frequency is large compared to the duration of the pulse, that means when the carrier frequency is large compared to the baseband signal frequency, then this entire term will vanish. So we we just ignore that and discard this part of the equation. So we are left out with this particular part of the equation, which is 1 by t cosine integral of the cosine 2 pi m minus n. Now what is integral cosine? It is sine, so it is sine 2 pi m minus n delta f t divided by this term, because we are integrating with respect to t. Apply the limits of the integration, which is 0 to t. When you apply t, the variable is t, so you get t here, and when you apply 0, it becomes sine 0, which is 0. So the second part of the term when applying the limits disappears. So we are having only the first part of the term when you apply this capital T as your limit. So we have this gamma mn factor to be equal to sine 2 pi m minus n delta f capital T by 2 pi m minus n delta f, and this capital T has come here. Okay, so now we are interested in finding what should be the delta f that will make this entire term 0, because if this entire term becomes 0, that means gamma mn, which is basically the inner product between the two frequency components, will become 0. So we want to make sure that we choose this delta f in such a way that this entire term becomes 0. And how to find it? We can calculate or plot this term, this whole thing, as a function of delta f, and find out at which values of delta f this whole thing becomes 0. And one quick observation by looking at the equation, if you see that if you put delta f to be 1 by 2t, right, if you put delta f 1 by 2t, then the denominator t and the numerator t will disappear, so t and t will go, and the 2 and 2 will also go, so you will be left with sine pi m minus n, right? So it is like it will be some multiple of sine pi, and multiples of sine pi would always be 0. Sine 0 is 0, sine pi is 0, sine 2 pi is also 0, sine 3 pi is also 0, because sines on the horizontal axis are all 0. So a quick observation of this equation tells us that if we choose delta f such that we can get rid of this 2 and this t, that will give us this entire term to be 0. So if we have delta f to be 1 by 2t, we will get this term 0, which makes this measure of similarity 0. That means the two carrier signals are going to be orthogonal with respect to each other. And since that is the delta f is the spacing between all the carriers, all of them will become orthogonal with respect to each other. Right, so as I said before, choosing the delta f value to be 1 by 2t would make this term 0, or we can also choose delta f to be multiples of 1 by 2t, which again would make all these angles to lie on the horizontal axis, which will all result in the sine component to be 0, so therefore the inner product would become 0. And that can be observed from this plot here, where the measure of similarity gamma mn has been plotted as a function of the frequency separation delta f. And what you see is that this inner product is 0 at 1 by 2t, is 0 at 2 by 2t, which is 1 by t, that is, it is 0 at all multiples of 1 by 2t. So 1 by 2t, 2 by 2t, 3 by 2t, 4 by 2t, and so on. So at all multiples of 1 by 2t, we get the inner product between the waveforms to be 0. That means a cosine signal of a certain frequency fc and another frequency which is fc plus delta f, such that delta f is 1 by 2t, will be orthogonal to each other, and we can create m such waveforms, m such carrier signals whose frequencies are separated by delta f equal to 1 by 2t or multiples of 1 by 2t. They will all be orthogonal with respect to each other. Okay, and we also notice from this diagram that the minimum value for this inner product occurs at 0.715 over t, and the minimum value that we get is negative 0.217. Okay, the implication of that we will discuss at in a later lecture, but for now what we are interested in is you just find out what are the values of delta f that will make the multiple carrier frequencies that we are producing, or the bandpass signals that we are producing, to all be orthogonal with respect to each other. Okay, so now with that information we can now have a general form, a general representation for Emery FSK signals, and we will also represent them in the signal space constellation diagrams. Because they are orthogonal, all of them are mutually orthogonal. That means they all lie on the axis of the m-dimensional space. So we've seen it for binary, where we had f1 and f2, so we can choose f1 as fc and f2 as fc plus delta f. So let me go back to that page where we had the equations for binary. So here, for example, we can say f1 is equal to fc, and f2 in that case will become fc plus delta f. So we have only two frequencies here, f1 and f2. Similarly, we can have for m equal to 4, where we have f1 is fc, f2 is fc plus delta f, f3 is fc plus 2 delta f, and so on and so forth. But the interesting thing is that for orthogonality we need to ensure that between fc, for orthogonality between fc and the second component plus delta f plus 2 delta f, this delta f should be 1 by 2t or some multiple of 1 by 2t. Only then we will have orthogonality. And since they are orthogonal, it means they all lie on some basis function on the axis, that is. So their geometric representation is going to be very similar to the geometric representation that we saw for the ppm signals. The only difference now is that in the case of ppm signals, they were baseband signals. So the distance from the origin on the axis was root E, the baseband energy. Now we have the bandpass energy, which is root EV. Everything else remains the same. So all the signal points, the bandpass signal points, are still lying on the axis of the corresponding basis function. Again, we have shown here for the three-dimensional case, because we can't depict four-dimensional on a flat sheet of paper. So we have it for a three-dimensional signal space, where we have the signals now lying on the axis, and basically this is a the basis function is a cosine signal. The basis function is a cosine signal whose frequency is f1. That's a basis function with a frequency f2, and that's a basis function which is a cosine signal with frequency f3, and so on and so forth. So we can write down the basis functions also for these signals. Okay, and since they are the signals are lying on the axis, the Gram-Schmidt procedure will result in these basis functions to be simply the signal divided by the norm of the signal, which is the square root of energy. And what is our signal? The first signal is square root of 2 EV by t cosine 2 pi FCT. That's our first signal. So we divide it by its energy, which is by its norm, which is root EV. So the root EV and root EV cancels out. All you're left with is root 2 by t. So root 2 by t cosine 2 pi FCT, that is your first basis function. And just for the notation, we call this as phi 0, phi 1 rather than as phi 1, phi 2, because we use fc plus m delta f. If you see m delta f, it makes it convenient to go for m from 0 to m minus 1 rather than from 1 to m. Okay, either way it's the same. It's just the notation and the way you interpret it. So similarly, for the second basis function, instead of phi 2 we are calling phi 1, because we call this as phi 0. It is the signal with fc plus delta f and divided by its norm. So, and since all the norms are equal, so we will have the second basis function defined in this manner. based on the second carrier frequency, right? So in general, we have all the basis functions to have this amplitude, which is √2 by t, and the cosine is fc plus m delta f. So for m equal to 0, it is fct. For m equal to 1 is fc plus 1 delta ft, and so on and so forth. So again, we get the similar concept like in the ppm signals, where the signals are all lying on the axis. They are all having the same distance from the origin, and that means the distance between any pair of signals is also equidistant, right? So that means the distance between any two signals is also given by 2 eV, where eV is the energy of the bandpass equivalent. Okay, right? I think that's the okay. So that is our conclusion, where we have discussed till now the bandpass multidimensional signals. And one easy way of constructing bandpass multidimensional signals is to have m carrier signals of each one having its own frequency. So that means we have carrier signal, cosine signal with m frequencies, so f1, f2, f3, f4, and so on. So we'll start with f1 as the carrier frequency fc, f2 as fc plus delta f, f3 as fc plus 2 delta f, and so on and so forth. And the whole trick is in choosing the value of delta f. If we choose the value of delta f to be 1 by 2t, that is the minimum value that you need to have, the minimum frequency separation that we need to have it orthogonal, or any integer multiple of 1 by 2t, then we will have, or we can ensure that all these frequencies are orthogonal with respect to each other. Okay, so we have seen how to create signals which are orthogonal in the frequency domain. So and since we can create m such signals which are all mutually orthogonal, that means their signal space representation will be an m-dimensional signal. So we have multi-dimensional orthogonal signals or waveforms. Okay, multi-dimensional orthogonal bandpass signals, because all the signals have a frequency centered around the carrier frequency fc, which is a large frequency. So therefore we have multi-dimensional bandpass orthogonal signals, which is a convenient way of creating multi-dimensional. So we call such a representation as frequency shift keying, or Emery frequency shift keying. Okay, so we conclude this chapter with this session, and in the next session we will start our new chapter. We will see how to best receive a particular signal and make decisions about the received signal in the presence of channel noise, and then we'll also evaluate the probability of errors and how to find the optimum receiver to minimize the probability of error, and so on and so forth. Okay, those will be topics for the next session, but for now let's quickly summarize and say that we have seen how to create baseband multidimensional orthogonal signals and also bandpass multidimensional orthogonal signals. And one simple way of creating bandpass multidimensional orthogonal signals is to have frequencies separated by a certain value, that is orthogonality in the frequency domain. And by choosing appropriate frequency separation, we can ensure that the signals are, or the frequencies are, orthogonal to each other. Okay, we'll have a session of discussion very soon. Thank you.